Hi girls, this video is for today's trig class and it's going to cover a couple of different things. The first thing that it's going to go over is a thorough graphing review. So if you feel like you need a really guided, in-depth look at tangent and then a couple of different kinds of cosine and sine graphs, then you want to make sure that you're taking it nice and slow through the video, really seeing where each of the key values comes from in the graph, and then how you put that graph on the page. So in your notes today, you've got some tangent graphs on the front page. Then you have a multi-stage transformation of sine. So it's going to be a longer process for graphing sine. Then you've got a multi-stage process for graphing cosine. And then last up, you've got some applications. So you want to use this video in a way that will benefit you. If you're feeling pretty confident already, I would just, for the original graphs for tangent, sine, and cosine, just check your work as you're going along. If you feel like you'd like really more thorough explanations as you're going through, then make sure you take your time getting through. Now for this video, it will probably end up being broken apart across a couple of links, just because that's been my experience with uploading to YouTube recently, is that due to the time constraints, it'll upload a lot faster if it's in a shorter video. So if it cuts out while you're getting through, just go back and look for the next link along the way. Now you might want to get some colors. I got some different markers and stuff for today, because when you get your graphs going, you want to be able to distinguish your original graph from the transformed graphs. So let's begin by graphing tangent. Now for each graph that we do today, we're going to want to graph the parent function, which is either going to be sine, cosine, or tangent itself, and then we're going to want to graph some kind of modified version. Now I'm going to try to turn the lights up just a little bit here so that you don't get too much of that shadow on the page. So hopefully that will make it a little bit better lighting wise. So for our tangent graphs, that's one that we need to have memorized. When you think about tangent, you want to think that on one side you're going to pi over 2. So I'm going to count off 1, 2, 3, 4 units, and I'm going to call this value right here positive pi over 2. In the opposite direction, 1, 2, 3, 4 units. That one's negative pi over 2. Now with tangent, those values are going to be what we call the asymptotes of the function. So I like to draw in my vertical dashed lines to show that the graph isn't going to cross those lines. Now the reason that tangent doesn't cross those lines is because if you try to take the tangent of pi over 2 or negative pi over 2, you really end up dividing by 0. So anytime you do tangent, on one half it goes to positive pi over 2, the other half it goes to negative pi over 2. So go ahead and break those up into halves, so you've got pi over 4 and negative pi over 4. Because tangent will always reach its amplitude value halfway between the origin and the asymptote on one side and the origin and the asymptote on the other side. So tangent is going to hit the point 0, 0, that's 1 point on the graph. And then for regular tangent, it's going to hit a value of positive 1 at pi over 4 and negative 1 at negative pi over 4. So if we graph that trend, and I know tangent can be a little bit tricky to graph, but it's sort of this S-like shape, that's going to be your original graph of tangent. Then you want to be able to graph changes, but you really want to know what that fundamental graph looks like before you start trying to make those changes. So let's go ahead and move on to this one here, 5 times the tangent of x over 4. So this value is your a term. That means that tangent is going to reach the value of 5 halfway between the origin and the asymptote instead of 1. So notice here, halfway between origin and asymptote, we hit the amplitude, which is 1. What this means is if I just had a 5, nothing else was changing, so it was just 5 tangent of x, then this one would be hitting 1, 2, 3, 4, 5 right here. So see how that would stretch out your graph significantly? So I know it's going to be stretched out vertically because of the 5. Then I have to account for what the x over 4 does. Now if you think about tangent as being divided up into pi over 2 on one side and negative pi over 2 on the other, you can just take your pi over 2, and then in this case, we can divide it by whatever this b term is. Now remember, if you have x over 4, that's the same thing as 1/4 x. So the b value in this expression is 1/4. So I can take pi over 2 and divide it by 1/4 here. And that's going to be the same thing as pi over 2 times 4, which in this case gives me 4 pi over 2, or 2 pi. So what that means is that instead of going from 0 to pi over 2 on one side, this transformed version of tangent is going to go from 0 to 2 pi. So we need to figure out what that looks like as far as scaling. If 4 units, 1, 2, 3, 4 is pi over 2, another 4, 1, 2, 3, 4, will put me at pi, and then 1, 2, 3, 4 puts me at 3 pi over 2, and then another 1, 2, 3, 4 over here puts me at 2 pi. So then I need to do the same thing in the opposite direction. I'm probably going to go off my graph, but that's okay. So 1, 2, 3, 4, that value is negative pi. 1, 2, 3, 4, this would be negative 3 pi over 2. And then if I go 1, 2, 3, 4 units, negative 2 pi is about right here. So that's where my new asymptotes are going to be. This time, let's use blue to show where the asymptotes are. And our asymptotes, again, just represent where the graph can't go past. So this is now the asymptotes for our transformed graph. These no longer have anything to do with the orange asymptotes on the page. So those guys are shifted out like that there. So now our transformed version of tangent, I'll go ahead and plot this one with purple. I know halfway between my origin and my asymptote is when I'm going to hit the amplitude value of 5. So halfway between 0 and 2 pi, that's pi. So at pi, I'm going to go up 1, 2, 3, 4, 5. Tangent's always going to be 0, 0. And then halfway this direction, so over at negative pi, I'm down 1, 2, 3, 4, 5 here. So if I go to connect my purple graph, notice that it's kind of stretched out in two different ways relative to the original black graph that we plotted. It is reaching up to a higher amplitude value, but also it's widened out this direction. So now this purple is going to extend up until it would hit the blue, and then it would continue on forever that way. And then this guy would go down that direction until it hit that blue there. So I do think it is a useful exercise to take a look at your graphing calculator and just make sure that this information that you see when you're looking at your page matches with what you see on your graphing calculator. So if you have a Casio, you'll have a slightly different process. But if I just graph my original tangent of x on one line, and then I graph 5 tangent of x over 4 on another line, I can kind of see how these graphs are going to be different. Now right now my scaling is a little bit funky on my graphing calculator, so it's going to be really tricky to see. But I can go ahead and zoom in so that I'm really seeing just 1 or 2 periods of each graph. So I'm going to change this window so my x-axis values go from negative 2 pi to positive 2 pi. And then I'm just going to change my y's. They're okay at negative 10 to positive 10. So this first graph that you see, this is your regular tangent that's being graphed. That's the first one that I input. Now this longer graph, that's going to be our newly graphed purple function. So in this case, this tangent graph, that one right there, corresponds to this black one that we graphed. This wide one corresponds to that purple graph. So see how tangent repeats after it jumps across the asymptote here, and then it goes up again, and then there's an asymptote, and then it goes up again. That's just because these graphs go on forever in both directions. So let's do one more of these tangent kinds of graphs. And this one, if you'll notice, our example up here had x over 4. That meant it went 4 times slower. This guy has 4x inside. That means it's going to go 4 times faster. So you do just want to keep in mind when you do your scaling, if you want to give yourself room to really see that comparison. So I'm going to scale my axes Slightly different than I did in this example, just so I have that comparison effect. So let's count off 1, 2, 3, 4, 5, 6, 7, 8. And let's call that pi over 2. So it's kind of like we were zooming in a little bit here. Then 1, 2, 3, 4, 5, 6, 7, 8. That's negative pi over 2 over in this direction. So for my original tangent function, that's where my asymptotes happen. So I can just sketch in. I'm going to do same color orange like I did in the previous graph. And the more you get to know sine, cosine, and tangent, the faster these graphs go. So here I'm at 0, 0, halfway in, so 1, 2, 3, 4. I'm at pi over 4. Halfway in this way, 1, 2, 3, 4. I'm at negative pi over 2. That's where we hit the amplitude value. So positive 1 and negative 1, and then you can just kind of connect those in the general tangent shape there. So notice it looks a little bit wider because we zoomed in. It's like we went like this on our screen to get there. So then we need to graph this new transformed function. So at this point, we're going to take a look at 3 times the tangent of 4x. So this 3 out in front, that's your amplitude. So remember what that means is that halfway between the origin and the asymptote, your graph would hit 3 instead of, in this case, it's hitting 1. So that's one change. Then we also have a period change because it's happening 4 times faster. So the cycle goes 4 times more quickly. So for tangent, you can think it takes from 0 to pi over 2 regularly. So I just divide by the b value. Pi over 2 over 4 is the same thing as pi over 2 times 1/4, which is the same thing as pi over 8. So I want to go pi over 8 in this direction, negative pi over 8 in this direction. So that's pretty easy to graph because pi over 4 is halfway to pi over 2. That's just fractions. Halfway to pi over 4, that's going to be pi over 8. So then I'm at negative pi over 8. Oh, I just realized this one should be a 4 right there. That was a mistake. So at pi over 8, that's where we're going to have our new asymptotes. So before we did our new asymptotes in blue, so let's stick with that color scheme. So this is going to be where my new graph is restricted. It's at negative pi over 8 and positive pi over 8. So I've got that restriction going on. And then when I go to graph my new transformed function, halfway between the origin, so this line right here, and the asymptote is where it hits the amplitude. So halfway is at this little tick mark, and that would be pi over 16 if I wanted to be specific, because that's halfway to pi over 8. So what I would do is go over, and then I'm going to be up 1, 2, 3 units there. I'm at 0, 0. Halfway to negative pi over 8, so negative pi over 16. I'm down at 1, 2, negative 3 here. So then I can connect that relationship right there. Now same thing, you can check out what's going on with that relationship on your graphing calculator. So if I go back to where I was graphing before, I can leave the tangent expression alone in my first line. Then I can change this guy to 3 times the tangent of 4x. Now you'll find your first graph that pops up, that's just regular tangent. That again is this black graph that we have right here. Then I've got all of this new information coming in, and notice how that's really hard to look at because that graph is happening 4 times as fast as tangent. So instead what we can do is change our windows so we're just looking from negative pi over 2 to positive pi over 2. So that way we see just one nice iteration of tangent, so that's our regular tangent graph. And then if we look at this narrow piece right there, that's that purple graph that we just did. So we can see the comparison between the two. That's your tangent graph, so that's some review there. Then we want to get into review of our sine and cosine transformations, so when we have many transformations going on. Now, whenever we begin these, you can just go ahead and begin by graphing your original sine function because that's going to give you a good basis to start from. So let's go ahead and mark off some key pieces of information here. Let's call every 2 units pi over 4, so every 4 pi over 2. So in this case, I'll go 1, 2, 3, 4. that value is pi over 2. Then 1, 2, 3, 4, this is at pi. 1, 2, 3, 4, 3 pi over 2. And then another 1, 2, 3, 4. Now we're at 2 pi. So when we graph our original sine, let's go ahead and just call this value right here. So we've got 1 tick mark as being equal to 1 and a negative as negative 1. It's always up to you how you want to scale, but if you're graphing your basic sine, you'll be at 0, 0. Pi over 2 will be at 1. Pi is at 0. Negative 3 pi over 2, or sorry, positive 3 pi over 2 is at negative 1. And 2 pi is back to 0. So if I graph my original sine function, it just makes that nice wave-like shape. And that's one of the graphs that we absolutely need to know by heart. So sine, cosine, and our tangent. Then we just go about making the transformations to the graph. And so I strongly recommend just taking each transformation one at a time and seeing how it affects the graph. So if you take a look at this equation here, this is telling you multiple things to change. There's a negative out in front, there's a 3 out in front, there's a pi inside, and there's a 2 outside. So that overall is 1, 2, 3, 4 changes that are going to happen relative to my original purple graph. So it's a good idea just to begin by going in order, so left to right, figuring out what each change causes then in the graph. So in this case, if I just begin by considering what the negative does to sine of x, then I can make the first transformation. So remember that a negative is just going to make each of the y values of your graph negative. So I would just write that out. Makes y values negative, and ultimately results in what we call a reflection. So it's going to flip upside down. So if I think about my starting place, this point 0, 0, the y value is 0. So that's not going to change. You can't make 0 negative. So that point will still be here. But this point, positive 1, is now going to be down here at negative 1. Again, 0 is not going to change, still at 0. Here, this negative 1 becomes positive 1. This 0 stays the same. So my graph just directly is reflected across the axis or flips upside down. So that's my first change that I want to make. Then I can continue to work left to right and identify each of those changes. And I'm just going to move down to the next graph so that we can really see each change distinctly. So let me copy down my scaling here. Pi over 2, pi, 3 pi over 2, and 2 pi right here. So with my scaling, what I can find then is that the next piece of the graph, if I move left to right, is going to be that 3. So now instead of just graphing y equals negative sine x, I can graph negative 3 sine x. So remember that this 3 out in front is going to stretch the graph out vertically. So we can say that we'll have a vertical stretch by 3, which you can think of as multiplying your y values by 3. So if I now go off the most recent graph, this green one, I'm just going to take each of the y values and multiply the quantity by 3. So for my first one, 0, 0, again, if I multiply 0 by 3, I'm still at 0. But then this guy is down here at negative 1. Well, negative 1, if I multiply that by 3, is going to send me down here to negative 1, 2, 3. So now I'm at this point. At pi, again, I'm at 0. Nothing's going to change. 3 pi over 2, I'm up at 1, 2, 3. So that's my new point there. Then at 2 pi, I'm back at 0. So I've got this point here. So if I sketch out this transformed graph, I'm stretching it out a little bit. So if I compare, I've got my original graph here. The negative sign flips it upside down to become the green graph. Then the 3 out in front stretches that green graph out vertically by a factor of 3, so I end up at the orange graph. So if we think about the transformations, we took care of this negative, we took care of the 3, and then we just need to continue moving along with the changes. So let's go to blue now for the next change, which is x plus pi. So remember that anytime you've got addition or subtraction inside of the parentheses, that's going to be a horizontal or left to right shift. And these ones are the funky ones because they're always opposite the sign that you anticipate. So if this says plus pi, what I'm really going to do is move my graph to the left by pi units. So you just have to think through your scaling, how that will move your graph. So I recommend going ahead and rewriting some information over here on the left. If I've got 4 units to the right making pi over 2, then 1, 2, 3, 4 units to the left will be negative pi over 2, and then 1, 2, 3, 4 more, that will be negative pi. So I just want to take each of these values and move them over a full pi unit. So if this guy's at 0, 0, now it's going to be at negative pi 0. This pi over 2 is now going to be at negative pi over 2, negative 3. This pi is now at 0. This 3 pi over 2 is shifted over here to pi over 2, and then pi is this 2 pi shifted pi units this way. So then I can connect those dots, and I've got the blue graph. So we flipped it upside down, we stretched it out, and then we moved it over this way. We translated it to the left. So we've got one last piece to account for. That was the plus pi. So now we've just got this plus 2 at the end. So let's go ahead and jump down to the final graph to create this last piece. And I'll go ahead and do that one in pink. So this one is going to be the final graph. Negative 3 sine of x plus pi. And then I've got plus 2. So here, adding the 2 out is just going to translate me up vertically. So all I need to do is take my blue graph, and everywhere I see my values, I'm just going to move them up by 2. Again, I need to give myself some scaling. So if I'm over here, 1, 2, 3, 4, that's negative pi over 2, 1, 2, 3, 4 more, negative pi, 1, 2, 3, 4, pi over 2, 1, 2, 3, 4, pi, and that's really all I need because I'm not changing my x values at this point, I'm just shifting it up. So this guy's at 0. If I move it up 2 units, well now it's at 2. This guy's down at negative 3, so if I move up 2, I'm going to be at negative 1. This 0 goes up 2 to 2. This is at 3, so it's going to go up to 5. So I'm at 1, 2, 3, 4, 5. And then my pi value is at 0, so it's going to go up to 2. So then I can connect to the pink dots here. And I'll see that I have my blue graph, but now it's just been shifted up vertically. So again, going over those transformations one more time. The negative flips my graph. Then once it's flipped, we stretched it out because of the 3. Then we shifted it left because of the pi. Then we shifted it up because of the 2. So if you just want to see your original sine graph and compare it to the transformed sine graph, again, your calculator is great to use, but you also want to be an effective user of the windows. So my regular sine function I can plot like this. My transformed sine function looks like this. Negative 3 sine of x plus pi plus 2. Now, regular sine goes from 0 to 2 pi. It's full cycle. This guy is going from negative pi to positive pi. So if I graph, I probably want to go from negative pi where one of them begins and positive 2 pi where the other one ends. So the first graph that comes up here, that's our regular sine. Then this next graph is the changed one. Now one thing I would recommend is changing your window a little bit. I'm going to change this y min to negative 2 and my y max to 6 just to see if I can get a better view of what's happening. So my regular sine just appeared here. That's regular sine from 0 to 2 pi. Then I've got this shifted graph here. So notice if I look from negative pi to positive pi, that's this piece of the graph here. So negative pi, then it comes up, and then it comes back to where it started. So I can always check with my graphing calculator, but you do want to play around with the window a little bit to make sure it looks good. let's repeat that process with our cosine graphs, and then we'll get into one application problem for tonight. So your cosine, remember, is very, very similar to sine. We always want to get down our pi over 2. 1, 2, 3, 4. You guys are going to get so tired of counting these off, I'm sorry. 1, 2, 3, 4. But your cosine, the only thing that's different from 2, 3, 4 from your sine is just that it's going to start at a different place. So instead of starting at 0, 0, it starts at 0, 1. So I just go ahead and make a point right there at 1. Then it just follows the same wave cycle. So I'm at 0 here, at -1 here, 0 here, and then back up to 1. So cosine begins at a peak. If you want to think of that top part as being a peak, then it comes down to the bottom and then it comes back up. So here we just got some changes to make about what's going to happen as far as how our cosine graph changes. So let's go ahead and break apart how many different transformations we have. We've got a 2 out in front, a 1/2 inside, and a -1 on the outside. So here we only have 3 transformations. Before we had 4, so that's a little bit of a nice change that there's only going to be 3. So let's read left to right. First, we're just going to account for the 2. Now remember, that's just going to be a vertical stretch anytime you're just multiplying out in front. So all of my y values are just going to go up by 2. So now I'm at 2 here, I'm at 0 here, I'm at -2 here, 0 here, and back up to 2. So the first change is just going to stretch the graph out by a factor of 2. Because my scaling's pretty condensed here, that doesn't look like a whole lot, but it's changing our amplitude by 2. Then we want to take a look at this 1/2 right here. So I'm going to move down to the next graph, and here we're going to plot 2 cosine of 1/2 x here. So again, I need where my values are going to happen. So I want pi over 2, I want pi, 3 pi over 2, and then another 4 units puts me at 2 pi here. So remember, anytime you have a change in the b value, that can happen on the outside, kind of in the cosine, or if I had parentheses around like this, either one would work. It means for both of them that the b term is inside of the cosine argument or expression. And so that's when you know that you're going to change how fast it goes on the vertical axis. So currently, cosine's period is 2 pi, but now we're going to divide that by 1/2. So now it's going to be 4 pi. So I have a little bit of an issue with my scaling here because my graph does not extend past 2 pi. So what I can do is just make this graph a little bit longer, or if you want to rescale your axis, that works just fine too. So if I got 2 pi over here, if I just do a nice estimation, this is going to be 3 pi and then 4 pi. That looks about twice the distance of 2 pi here. So the only thing that's going to change is that my graph is going to stretch out by that additional factor. So that means originally this brown graph is at 0, 2, so that stays the same. But my first 0, the first time it comes down, happens at pi over 2. This is going to be twice as long. So it takes, instead of going to pi over 2, it's going to go all the way over to pi. Then this next value at pi, that's going to happen down at 2 pi, so it reaches that should be a -2, not a -3. Then it comes back to 0 at 3 pi and back up to 2 over here. So if I sketch out that extended graph, it's going to look like this. So notice from our original black graph, it's stretched out vertically by 2, and now we're stretching it out horizontally by 2 because it's half as fast. So this is a period value change, which causes a horizontal stretch or shrink. In this case, it's going to be a stretch because it takes a wider distance to get through the full wave cycle. Then we've got one more change, you guys, and that's going to be the -1 on the outside. So this one's pretty easy to do just from the graph that we're on. So let's go ahead and do this here. 2 cosine 1/2 x -1 on the outside there. So all of our values are just going to move down by 1 because it's just a subtraction of 1. So let's go ahead, and I need to extend that axis out again, just so we can, oh, never mind, we're gonna do it on the same graph. So I'm just gonna move down each of my values by 1. So this guy's at 2, now he's at 1. This guy's at 0, now at -1. This one is shifting down to right here. This one shifts down to -1, and this shifts to +1. So we can stretch and connect these peach dots here. So notice that that graph looks almost identical because it's just shifted down 1 unit. So here, stretched out vertically, stretched out horizontally, shifted or translated down vertically. So that's what we want to write here. Translated down vertically. So I hope you're feeling a little bit more confident with your sine and cosine and tangent graphs, but we still have one more review day with these, so if you have any remaining questions, that's going to be what Thursday's for. The last thing that we're going to cover today is information about how we use trig functions for applications. And even though this is kind of the last piece of the video, you may have to finish up just a little bit of it at home tonight, it's probably the most important part. Here, this says we're doing our extended graph work and involving real-world applications of sine and cosine graphs. So the reason that we want to spend a lot of time in this kind of work is that sine and cosine are just really essential functions for modeling the real world. Here are some of the things that can be well described by trig functions. The transmission of electromagnetic radiation, so that's going to be things like UV rays from the sunlight. That's going to be things like gamma rays from outer space. That's going to be the visible light that you and I see. It's going to be ultraviolet light that some animals would interpret or infrared light. It's going to be the radiation that people receive if they're receiving radiation treatment for cancer. Anything that you can think of that involves electromagnetic radiation is going to be transmitted by a sine or cosine-like function. So really important, if you think about how your electric devices operate, so your computers, your tablets, they all rely on electricity. All of that's going to follow this kind of pattern. Other things like temperature profiles, when temperatures in a city hit a peak and then a valley, so they hit a high in the summer, a low in the winter, that's a trig function. Biorhythms and cycles, so the way our heart rate changes during the day, our circadian rhythms of sleeping, that's all modeled by trig functions. Ocean tides, so ocean tides reaching a high tide and a low tide, that's a trig function. And then animal population, so some animals will migrate, which means there's a high population at one time and a low population at another. That's a trig function too. So much of the real world is modeled by trig functions that in order to make accurate predictions about a lot of things that are represented in our day-to-day life, we need them. So we're going to take a look at a nice example involving temperature, but we'll keep coming back to these. And then section 14.5 is going to be all about applications, so all about where these are used and why they're used. So let's take a look at this example. It says the number of hours of daylight in Rhode Island is given by the equation below, this one, where x is the number of days after January 1st. So we've got this equation and it looks really bulky. It says y equals 3 times the sine of 2 pi over 365 times x minus 79 plus 12. Lots of transformations happening there, right? This would be an amplitude, vertical transformation. This guy is going to be a periodic transformation. This is going to shift you horizontally. That's going to shift you vertically. But even if you don't know all of that, you can answer the questions A and B. A says, what's the amplitude? So your amplitude is just 3. In this case, if we're talking about number of hours of daylight, what you can kind of picture that meaning is if you're going to go up 3 and then down 3. So there's going to be a difference, positive 3 minus 3, that's a difference of 6 total hours. So over the year, there's going to be a change of 6 hours between the one day that has the most sunlight and the day that has the least sunlight. Then the period, remember your period value, if we go to calculate it, P is just going to be 2 pi over B. B is the number out in front here, so 2 pi over 365. So that's going to be 2 pi over 2 pi over 365. Dividing by a fraction, that's the same thing as multiplying by its reciprocal. So 365 over 2 pi. Your 2 pi's will cancel, and you're left with 365 days. Now, you guys, it makes sense that the period, or the length of time it takes for this cycle to repeat itself, is 365 days, because that's the number of days in the year. So you're going to hit a maximum once when the Earth is closest to the sun, right? And then a minimum when it's furthest away and facing away. So then once we know that information, we can start to make predictions with the equation. Here, this says how, and that should say many, not any, hours of daylight are there on the longest day of the year. Well, this is where I would kind of need to go to my computer, because I'm pretty sure that the longest day of the year happens on June 21st or June 22nd. But I don't know for sure, and I have no idea off the top of my head how many days it is after January 21st. So I can go to Google, because Google knows everything, and I can just type in longest day of the year. That's going to be the 21st. So then I can say, how many days is June 21st after January 1st? And I'm sure somewhere on Google, it'll tell me how many days there are between 2 days. So it just asks me to put this information in. So I pick my June values. And if you want to find something like this on your device too, that works out great. And then I'm calculating, and it tells me that's 171 days. So longest day is June 21st. That's 171 days after January 1st. So all I do is take 171 and I plug it in for x. So that's going to tell me y equals 3 sine 2 pi over 365 times 171 minus 79 plus 12. And I just need to plug that whole thing into my calculator. Kind of bulky, but we can do that. Here, 3 sine 2 pi divided by 65 times 171 minus 79, and I want to be careful with those parentheses, plus 12. So I get a value of 13.52 hours, and that's going to be of daylight. And so that probably doesn't seem that long, right? I mean, 13.52 hours. If the sun came up at 6, it's going to be going down at 8. So you can imagine there are going to be certain places in the world that are going to have longer than that amount of daylight, certain times that are going to have less. Then it asks me, how many hours of daylight are there on the shortest day? So same thing, I'm not great with my longest and shortest days, but I'm pretty sure the shortest day is going to be in December, I think December 21st. So I can confirm that. Shortest day of the year, yeah, December 21st, that's your solstice day. And then we can do the calculator. So if we're going between January 1st and then we go down to December 21st, I'm just using that online calculator here, it tells me that that is going to be 354 days. So here, December 21st, 354 days is our x value that we input. So we use the same equation, y equals 3 sine of 2 pi over 365 times I'm plugging in, and this is all happening inside the parentheses, so that's why you want those extra parentheses here, 79 plus 12. So I plug that whole thing into my calculator. 3 sine parentheses 2 pi over 365 parentheses 354 minus 79. Close your parentheses twice and add 12. And that tells me there are approximately 9 hours. That's pretty short, right? That would be like 9 to 5 of sunlight. Last thing it asks us to do, probably the most challenging, just looking at the equation, is going to be to graph the function for one period. And in this case, it says beginning on January 1st. So go ahead and give yourself an XY graph in the space that's provided down here. And let's talk about some of the best practices for putting together a graph when there's so much funky stuff going on visually. So my pen didn't want to work there. If we go to graph this function, what you want to keep in mind is what information you're going to have when you're starting on January 1st. So January 1st, your x value is number of days after that. Now we know that if we're starting on January 21st, one cycle is going to take 365 days to complete. So you can mark that off. Here is 365 right here. And if I break that apart into 4 even pieces, I can figure out where the max and minimum values are going to occur. So 365 over 4 is 91.25. So I can break this apart into even pieces here. And that means I'm going to have 1 at 91.25 here, 1 at 82.5, and then if I add that again, 1 at 273.75. So then I just have information about what my graph's going to look like. And it can be a little bit tricky to figure out which piece to start off with first. So going off of that same equation here, I know that it takes 365 days to make one full cycle. But this information is telling me that I need to start in 79 days. So that means that my first value, if I go ahead and just find 79 instead of starting at 0, that value is going to be from your 3